Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be talking about solving compound linear inequalities in two variables. We've done this before in one variable, but now we're going to apply it where we have multiple inequalities with multiple variables. We're going to start by talking about what a system of inequalities in two variables is. I want us to think back to a system of equations. The definition for a system of inequalities is pretty much the same thing. We have multiple inequalities constraining two variables. So we have multiple inequalities before we have multiple equations that affected the different variables. They constrained them, meaning they put certain conditions on these variables. So here we're going to take two inequalities and we're going to say that the two variables x and y are affected by these inequalities. Now I want us to differentiate when we talk about a system of inequalities from compound inequalities. A system of inequalities and compound inequalities are pretty much the same thing. Except when we refer to compound inequalities, we're more so specific with how we want to form the solution set. Compound inequalities are where we have multiple inequalities, just like before, and we are basically restricting what the variables can be. We're constraining the variables to specific solutions. However, when we get the solutions, we're making them either the union and intersection of other solution sets. So we're applying this very specific technique of how we're going to combine the solutions, okay? But that's the idea. We're going to think of systems of inequalities and compound inequalities really as interchangeable terms. What I'd like us to do now is actually go through a problem where we have a compound set of inequalities, and we're going to see how we can determine the solution set for the compound. First up, let's take a look at this situation here. We have two linear inequalities. X minus 3y is greater than 3, and y is less than negative 2x plus 4. What we should do here is graph both of these. Because when it comes to really understanding the solutions to linear inequalities in two variables, the best way of understanding them is by looking at a graph. It's very difficult writing them in set notation, so why don't we use a graphical representation? I'm going to graph this inequality in blue. So y is less than negative 2x plus 4. Let's see, I'm going to go up 1, 2, 3, 4 units right here. And then let's go down 2 units. 1, 2, and over 1. 1, 2, and over 1. And there we have our... let's see. And there we are using our slope to help us find what the line will be. Let me try to draw this line first. Okay, not bad. But you'll notice that this problem's inequality does not include the endpoints. It doesn't include the line. So what we need to have is a dashed line. So I'm going to try to erase sections of this graph to make it look like the line is dashed. Okay. So here's the one line, and why don't I go ahead and in a different color, maybe red. Actually, you know what, I'll use green for this. I'll graph this line. Well, the problem is this isn't solved for y, so let's do that. I'll say x minus 3y is greater than 3. Let's subtract x from both sides. Negative 3y is greater than negative x plus 3. We'll divide both sides by negative 3. And we end up with a y, a positive 1/3 x, and a negative 1. You'll notice we need to flip the sign because we've divided by a negative, so we have to flip the sign here. And this is what the inequality becomes. So let's plot the y-intercept. And then let's go up 1 and over 1, 2, 3. Maybe go down 1 and back 1, 2, 3. Okay, let's plot this line. Not bad. And again, since this sign is not a greater than or equal to or a less than or equal to, what we need to do is have a dashed line. It doesn't include the endpoints with it, so we want to have a dashed line. All right, we have just graphed what I like to call the boundary lines. Now we need to find their solution sets. We need to figure out for each of the graphs, where are their solutions? So let's start with maybe the green graph. Let's figure out, are the solutions to the green graph on this side of the green line, or are they on this side of the green line? To do this, we pick a test point. Why don't I test the point 0, 0? So I'm going to say here, test 0, 0. And let's see if this works. 0 minus 3 times 0 is greater than 3. Well, this whole side is just 0, so 0 is greater than 3. Is that true? Well, no. Obviously, that's a false statement. So 0, 0 here is not a solution. Therefore, if one of the points on this side of the graph is not a solution, that means all of the solutions are on the other side of the graph. So let me go ahead and try to shade in carefully this side of the graph. Let me see if I can do that rather lightly, just so we can still see what's going on. Okay, so imagine that blue line isn't there. Everything shaded in green is a solution for this inequality. Now, let's go back to the blue equation, and let's pretend like we're just working with that. So let's see where the solutions are for the blue equation. Either the solutions are all over here, or they're all on this side. So I'm going to test the point 0, 0. I'm going to test that by plugging it in to the inequality and see if we get a true or false statement again. So I'll write that down here. Test 0, 0. I always like to identify what points I'm testing. So 0 is less than negative 2 times 0. Let me write that a little neater. Plus 4. Well, that's just 0. So 0 is less than 4. That's a true statement. 0 is less than 4. So I know that this point is a solution. So if this point is a solution, then that means all the other points on this side of the graph are solutions. So let me go ahead and I need to shade in this side of the graph. And again, I want to do it light enough so that way we can see everything that's going on. All right, that should be good enough. So we have now the solution set for the blue inequality and the solution set for the green inequality. We can see a visual representation of all the solutions for the one and all the solutions for the other. Now what we need to do is try to figure out how can we solve the system or the compound. We have the word and here. Remember, and means you want a solution to be true for one inequality and the other inequality. You want to pick an x and a y coordinate, meaning you want to pick a point, right, somewhere on the graph, some x and y coordinate, that if you plugged it into both inequalities, it will work. It'll give you a true statement. So I want you to pause the video, and I want you to take a minute to see if you can identify where there are points that will be solutions for both of the green and blue inequalities here. Where do you see points that will work for one and the other? Well, hopefully you're saying it's the area where they overlap. Remember, when you see the term and, it means the intersection. And meant the intersection, the area where the two graphs overlapped. So that would be this area of space right here. everything trapped in this little area, and again, it goes out for infinity, but everything on this, I guess you could say, quarter of the graph. Again, everything right here just works for the blue, everything right here just works for the green. None of these values are solutions for either of them, but everything over here will in fact be a solution for both of the inequalities. So if I wanted to show this and I wanted to be rather neat with it, I could go ahead and just erase the shading that I didn't need. Or you could just show where the overlap is. And with that, we'd have a little graph to show where, in fact, our solutions are. This is the way we're going to go about showing and demonstrating what the solution set is for these compounds. Let's come up with a little process explaining what we did here. To start off, when we come up with a process, let's first identify that we should graph both inequalities. You want to graph both inequalities, and we will then graph the solution sets to each inequality. So not only do we graph the lines, but we also go ahead and graph their solutions. What we then need to do is determine how we want to go about in combining the solutions. If it is an AND compound, take the intersection. Let me write that a little neater. Take the intersection. If it is an OR compound, remember, that is where you want to take the union. Once we have both of the inequalities graphed, we can then decide whether or not we want to include the intersection or the union, and we can present our graph that shows what in fact the solution set for the compound would be. What I'd like us to do right now is to take some time to practice this process, practice graphing multiple inequalities, and shading all of their solution sets. Then, once the solution sets are shaded, I want you to go ahead and decide what you want to do for the different compounds. Do you want to take the intersections? Do you want to take the unions? And decide what that would look like for these problems. So go ahead, pause the video, and give these problems a try. All right, well, hopefully you're starting to get the hang of this. Take a look, make sure that you got the correct lines graphed. You'll notice in the first problem, I actually went and solved one of the inequalities for y, and I plotted the line. You'll notice for the first problem, I have solid lines, and for the second problem, I have dashed lines. So make sure you have the correct lines graphed, and then once you have the boundary lines set, go ahead and start testing to see where you're going to shade the solution sets. All right, well, hopefully you're able to get the correct shading down for each of these graphs. You'll see where we have the overlap. Now, we want to indicate what the solution is going to be, not only just for each of the individual inequalities, but for the compound as well. So, both of these compounds, you'll notice, are AND compounds, meaning that they are requiring us to take the intersection of the sets. So, I'm going to go ahead and try to shade in red, let's see if this helps out at all, where the solution set is for each of these compounds. So, first up, right here, is the one overlap area. And right here, this small upper portion is the overlap area as well for this graph. So these two areas that I just highlighted in some red Basically, those are the solution sets. Those are the areas that contain the x and y coordinates that if you plug them into both inequalities, it will work for both. It has to. That's what the and constraint means. It means it's got to work for one and the other. Let's go ahead and take a look at another problem, slightly different. You'll notice in this situation, we're dealing with an OR compound. I want you to go ahead, work this solution out, graph both of the lines, see what their solutions are individually, and then decide what's the solution to this OR compound going to look like on the graph. Alright, hopefully this problem was making sense to you, and hopefully you were able to generate these graphs. You'll see I drew the boundary lines and I made them solid lines because they are being included in these problems. Once I solved each of the inequalities for y and graphed them, I then ran a test point for each of these. Basically, I just tested the point 0, 0. I saw that it was not a solution for the first inequality, so all of its solutions would have been on this side of the line. Then I tested it for the other inequality and found that it was true, so all the solutions for the green inequality are on that side of the line. What we need to do now is determine what the solution is to the compound. Here we have the compound OR, meaning we want the set of all points that will be a solution to the one inequality or the other. Remember, with OR, we want to take the union. We want to take the union of each of these sets. So, if we're looking graphically at what the solution set would be, basically all of that. The union is everything that's shaded in. Okay, we're just including everything with the union, while the intersection was the overlap. So keep that in mind as you work through these problems. If you have any questions or comments, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video, or if you have any questions or concerns. And until next time, take care.